Here we have two general points, and I see that if I move the points then my line changes. But all I need is 2 points to define a unique line. And we looked at using the gradient point formula to describe those lines. If we have a quadratic, then we need 3 points to define the quadratic. So I see if I move these around, there is a quadratic that will perfectly go through them. We might notice one thing: if I drag this point, trying to keep the quadratic as the vertex, so see how I'm dragging it along my quadratic, dragging it along, trying to keep it exactly the same. If I drag it precisely on the vertex, well then it looks like I've only got 2 values, and that's defining my quadratic or my parabola. But if the point I know is the vertex, a special point, well then I just need to know the vertex and then one other point to define my quadratic. We had a look at that last lesson, so parabolas in vertex form. So here we see the general form y equals a bracket x minus h all squared plus k. So this is the situation where a equals 1, h equals 0, and k equals 0. So this is just y equals x squared. I'll see here if I change the value of k first, I get graphs such as y equals x squared plus 2 or y equals x squared plus 4. So changing the value of k simply moves my x squared graph up or down. We call this a translation along the y-axis. You'll look at this a lot in your extended mathematics and your methods pathway. If I change the value of h, I see my graph translates along the x-axis. So if I translate down and then to the left, I've still got this x squared shape. It's exactly the same shape as before, however its position has changed. If I change the value of a, however, the shape does change. The greater the value of a, the narrower it appears. When it becomes less than 1, it becomes shallower. And then for negative values, I see my parabola opens up downwards. Now, any parabola can be written in vertex form. So here I have the graph y equals x minus 3 times x plus 2. So the vertex here should be the average of my x-intercepts. So minus 2 add 3 is 1, divided by 2 is a half. So then if I move my vertex to a half, and then down to match the vertex of my other graph, that looks pretty good. That's fairly close. Now my value of a should be 1. So I see that manipulating the values of a, h, and k, I get an exact match for my other quadratic. Sorry for the bashing, I believe my cat just jumped up on the bench upstairs. Sorry about that, we're trying to keep the cats off the kitchen bench, because the other day I came home from work and there was some fried rice on the bench and I decided to have some. It wasn't until afterwards that my kids decided to tell me that the cats had jumped up and eaten some, and they thought that was hilarious because, as they told me, Dad, cats lick their bums, and I didn't find that so funny. Now back on topic, we just saw that any quadratic can be written in vertex form. We can write a quadratic in vertex form by completing the square. So now we're going to have a look at repeat that process again that you've seen in your extended mathematics class, and then look at how do we sketch from that form. So let's have a look at this example. Here we have y equals x squared plus 6x minus 4. When we write a quadratic in vertex form, we'll find that x only appears in one location. To achieve that from this form, we need to complete the square. Now you've been shown how to do this a number of ways, and the link to the actual square and physically completing it. This is how I think of it. If we're going to have x in one place, we must have an x plus 2 or 1 or 6 in brackets all squared. The role of this part of the expression here is to account for the x squared and the 6x term. So when I complete this, it'll be a perfect square. So when I expand, I'll get an x squared term, but I'll also get a middle term that everyone forgets about. To get a middle term of 6x, I need a plus 3, because I'll get a 3 times x multiplication occurring twice, giving me 6x. If you're not sure about this step, you need to go back, practice, do some boxes. When I expand this perfect square, I get x squared plus 6x plus 9. Now the role of this part of the expression is just to take account of the x squared plus 6x. I don't want the 9 there, so what I'm going to do is take 9 away. So now this part of my expression is equal to x squared plus 6, and you see I've kept the minus 4. So now, tidying this up, we get x plus 3 all squared, take 13. Let's have a look at how to sketch this. Last lesson, we looked at how to get the vertex from this form. Here we have the vertex, or the turning point, at minus 3, minus 13. So remember, it occurs for the x value that makes the bracket 0. That will give me the smallest possible value out of this equation of minus 13. In this example, my parabola will open upwards because my dominant term is positive x squared. Next, the y-intercept is when x equals 0. I can get that most easily from my expanded form. I see it is y equals minus 4. I could also substitute in x is 0 here and get 3 squared, which is 9, take 13, which is minus 4. Now for the x-intercept. The x-intercept is when y equals 0. So here I've subbed in y equals 0. And this is relatively straightforward to solve because I have x in one position. So to solve here, what I need to do is work in the reverse order of operations. So what happens to x after I substitute in here is I add 3, then the result is squared, and then 13 is subtracted. So we're going to work backwards, reversing that to solve for x. So the first thing I'll do is add 13 to both sides. Here, my next step now is going to be to take the square root. And I can do that because the left-hand side is positive. I'd find at this step here, if I had, say, negative 13, I couldn't take the square root of negative 13. That would mean there would be no x-intercepts. But here, let's take the square root. So I see 2 values because when I take the square root, I could get a positive or a negative solution. 13 isn't a square number, and it doesn't have any square factors, so I cannot simplify this third. Next, I'll subtract 3 from both sides. So I see my 2 x-intercepts of minus 3 minus the root 13 and minus 3 plus root 13. Now in the test, when you complete a question such as this, will probably be nice and give you a square number. But I wanted to show you this example to show you that in general, this process can always be done. Now, given this information, let's do the sketch. So first I'll locate my turning point, minus 3, minus 13, perhaps here. Next my y-intercept of minus 4. So I can see here that one of my x-intercepts is going to be negative and one of them is going to be positive. Looking back down at my x-intercepts, minus 3 plus 13, this is a positive number because remember the square root of 13 is bigger than the square root of 9, which is 3, so definitely a positive value. So we can put both of these values on the graph. Before I do so though, I'm going to sketch in my quadratic. So there's the complete sketch. But one nice thing here, if I draw in the line of symmetry, well then my x-intercepts should be an equal distance from this line of symmetry, which is x equals minus 3. So quite nice from writing the intercepts in this form is that I see this distance here from the line of symmetry is root 13 in both cases. So going to the right, I'm starting at minus 3 and adding in root 13. Going to the left, I'm starting at minus 3 and subtracting root 13. Now quickly recapping the steps here. First, there's completing the square to get the quadratic into vertex form. Once it's in vertex form, you can write down the position of the vertex, the shape you'd get here from the expanded form or the vertex form, the y-intercept, that's when x equals 0, but make life easy, just read that off the expanded form. For the x-intercept, sub in y equals 0, and then the big idea here is x appears in one spot, so you can use your reverse order of operations to solve here. What happens to x? You add 3, the result's squared, and you take 13. So work backwards. Add 13 to both sides, take the square root, remembering there's two different solutions, then subtract 3. Important here to realise that it's the plus or minus that gives you two solutions. However, you'd find if there was no term here, it was 0, my first step would be to take the square root of 0, and I would only get one solution. If this term was a positive value, I'd find on the next line I'd have a negative number here, which I can't take the square root of, and that's when you get no solutions. So this is a little bit trickier mathematically, but it is a lot more powerful because we can sketch any quadratic this way. We don't have to rely on it going through the x-axis.